In this video, we take a look at another a testing technique, another method to determine if a series converges or diverges. So what I want to do is look here at what we talked about before as our harmonic series, and we'll be able to classify this a little bit better too. And we're going to actually show here first that this indeed diverges. And this is the series where I add 1, 1/2, 1/3, 1/4, so on and so forth. The denominator is just increasing by 1 every time. And this is contrary to what we might think from our nth term test, right? If you remember from last time, if I take the limit of 1 over n as n goes to infinity, 1 over n goes to 0, right? But remember, the nth term test was for divergence, and it only works if the limit was not 0, okay? So it's a little ambiguous here. This series does indeed diverge, right? And I want to show that. I want to show the harmonic series diverges. And to do that, what I'm going to do is I'm going to relate this to the function f of x is just 1 over x. And since I'm working with this series, I'm only dealing with positive integers, n, so I'm going to be working with this function for positive x values, okay? So when I'm thinking about it as a function, I'm letting x be anything as long as x is positive. I'll draw a graph of this and use that to my advantage here on the next slide. But what I want to do is show why I can relate these things, in such a nice way. 1 over x and 1 over n, of course, look very familiar, just switching letters there. Let's plot a couple points. Let's put a table of values here. If I set up a table for x and f of x, where x is 1, 2, let's go all the way through 7 here, then the function value is just 1 over the x value. And of course, the series is just the sum of those guys, right? It's the sum of each of these added together. Okay, so it's a small distinction from the series to the function. The series has only positive integer inputs, and the function has, all real numbers as inputs. Okay, so what I want to do is I want to graph I want to graph this function f of x, and I want to relate that to the series, and maybe use what I know with calculus to help me determine whether this series indeed does diverge. Okay, so here we have my function 1 over x and just an xy axis here. So I'm just going to plot those points that I had on my graph. I'm going to increase the scale a little bit. So say 4 blocks is equal to 1 here, so that's 1, 2, 3, 4. Then the points that I have are 1, 1, 2, 1/2, 3, 1/3, 4, 1/4. So my curve should just follow through those points like that. Okay, so I've plotted those points in green. Of course, I had more points on my table there, but I just use a couple here, and I think it gets the point across. So this function indeed has an asymptote at 0. I'm not so much worried about that as the series that I'm comparing it to or relating to starts at 1. Okay, so what I want to think about here in a calculus sense and how that relates to that series 1 over n. 1 over n, the series, was the sum of all of those y values, right? 1 plus 1/2 plus 1/3 plus 1/4. Okay? That's really like the heights here, the heights of those points, the y values. Notice that the widths from one x value to the next, right? Those x distances are all 1. 1, 1, 1. So what I'm going to do is I'm going to create boxes with the left endpoint here. We're actually going to kind of look at almost like a Riemann sum, a box with the left endpoints using those actual heights there. So what I really have, this first box has a height of 1, the second one has a height of 1/2, the third has a height of 1/3, and the fourth has a height of 1/4, so on and so forth. The widths are all 1, so the areas of those boxes are really just the heights, right? 1/2 times 1, 1/3 times 1 is the length times the width, or the width times the height, however you want to look at it. If I add all those areas up, that's the same as the value I get from the harmonic series. right? 1 over n. 1 plus a half plus a third plus a fourth. That is compared to the area under the curve here in pink of 1 over x, right? So I have this relationship between the areas of my blocks or my rectangles and the area under the curve. And I'm going to use that to determine whether this series converges or diverges. In fact, like I already mentioned, it diverges. I want to show that. And this will pave the way then for what we call the integral test, right? Because the integral is going to help me achieve that area under the curve, okay? So the area of my blocks, then, the area of these rectangles, is really just the harmonic series, right? It's just the sum of 1 over n. It's the sum of the areas of those rectangles, and those areas are the height times the width. The area under the curve is our integral of 1 over x dx, starting at 1 and going on forever, right? That's an improper integral. So I'm going to have to use the techniques we talked about before to evaluate that. And we already have an idea of which one of these two, are these the same, right? Are these values the same? Is one larger than the other? Well, if you look at the shaded area there, the pink area, the area under the curve, is definitely less because the green shaded regions always are above the curve, right? Because of the way I'm using those left endpoints. So I can assume that this sum is actually larger than the integral because of these extra bits here. So what I'm going to do now is I'm actually going to evaluate this integral because that's the part I know how to do. I can just add up all those numbers forever and ever, but I want a way to compare that. We can evaluate this improper integral, and that's with the limit as t goes to infinity of the integral from 1 to t of 1 over x dx. We know the antiderivative of 1 over x is our natural log function. So I take a limit of natural log of x as t goes to infinity when I evaluate natural log of x from 1 to t. So I plug in t, subtract what I get when I plug in 1. Plugging in 1 for natural log of x is 0. And as t goes to infinity, of natural log of t, natural log approaches infinity. So what that implies is really that my sum is larger than that integral, and that integral is approaching infinity. My sum is larger than infinity, right? It's infinite is basically what we can say. Therefore, the series diverges because it's larger than infinity. Adding those numbers up, I'm going off to infinity, okay? And that's not necessarily clear by just taking a limit of this 1 over n like we did on our nth term test. So please be aware that that distinction must be made. I can't just take a limit of what's inside and expect to know the answer. I know that limit. Sometimes that helps me tell whether the series diverges, but not all the time. And like I said, this paves the way for what we call the integral test. So this test has some criteria, and we need to go through those things, and we'll have to show those when we work through an example. But it's really mostly straightforward. It says the following here. If f is a positive, continuous, and decreasing, those are our three criteria, for for x is larger than or equal to k, and my a sub n, my nth term, is the same as f of n. So right, if I plug in n to my function, that's the same as looking at the nth term, or what's inside my sum. Then I can say the following thing. The series starting at k of a sub n and the integral from k to infinity of f of x dx either both converge or both diverge. Okay, so this is a test that tells us there is kind of a matching thing. We'll see some others, or like geometric series. We had convergence for a specific common ratio, right? We were able to say, oh, if r is less than 1 in absolute value, we converge. This test, and a few others we'll talk about, is a little different. We have convergence of both the integral and the series, or divergence of both the integral and the series. Okay? These three criteria, positive, continuous, and decreasing, it suffices to look at f of x and determine if it's positive continuous, and also if the derivative is defined and negative on the interval of k to infinity, then the integral test can be applied. Okay, so that is enough for us to apply the integral test, right? We're able to show very quickly that the function is positive and continuous. If the derivative exists on the interval from k to infinity, then the function has to be continuous there. So having the derivative defined and negative is enough. Let's do an example here. Determine whether the sum from 1 to infinity of n over n squared plus 1 converges or diverges. So I'll remind you of those three criteria as we go through this. Let's try to apply our integral test here. Now, how do I know I want to apply the integral test? It's kind of like a last resort. Well, so far we know about geometric and telescoping series. We also know the nth term test. Okay, if I were to take a limit of a sub n there, or n over n squared plus 1, I would get 0. The nth term test is not satisfied here. It does not work. It's inconclusive. That nth term, or that series there, is neither telescoping nor geometric, so none of those quick rules apply. So this is kind of very similar to, in Chapter 8. You're looking at a series and you're trying to determine which method you need to use, very similar to looking at an integral and determining which method you need to use. So I'm stuck with integral tests, kind of the way I feel about it. So I look at f of x as being x over x squared plus 1. I need to show that that function is positive on the interval from 1 to infinity. And that's a relatively simple thing to do, since the denominator, x squared plus 1, is positive. And since x is bigger than 0 on the interval from 1 to infinity, then yeah, I'm taking positive numbers and dividing them by positive numbers. This is a positive function. The second is I have to look to see if f is continuous on my interval. And again, not usually a difficult thing. X squared plus 1 is never 0. I don't ever divide by 0, take square root of a negative. There's no breaks or jumps. There's no discontinuities. No discontinuities on the interval from 1 to infinity. Good. The third is I have to determine that f is decreasing on the interval from 1 to infinity. And that's where that derivative comes in. I take the derivative as f prime less than 0. That's what it means to decrease. So the derivative here, I have a quotient with respect to x. I'm going to use quotient rule, right? So my derivative, low d high, less high d low, draw a line square below. This simplifies to 1 minus x squared over x squared plus 1 squared. Is this negative? Well, the denominator is squared. It's always positive. So all I really need to look at is the numerator. Is the numerator negative? Well, 1 minus x squared is negative when x is bigger than 1, right? When x is 1, 1 minus 1 is 0. That's not negative. But for anything after 1, 1.1, anything beyond 1, that numerator is negative. So the derivative is negative, which means I can apply my integral test. The three criteria are satisfied. The integral test applies. Okay. So I'm going to set up and apply my integral test here. I look at this guy, and I set up then the following integral from 1 to infinity, k to infinity, of replace n's with x's and integrate. Okay. So, since this integral is improper, all of these integrals with the integral test will be improper. I use a limit as t goes to infinity, the integral from 1 to t of x over x squared plus 1 dx. This is a quick little u sub, right? If u is x squared plus 1, then du is 2x dx, which means I have the integral 1/2 out front and du over u. This is a natural log antiderivative. Right, so similar to the harmonic series, that when we apply the integral test, this integral requires the use or results in a natural log. Okay, so this is then the limit as t goes to infinity of 1/2 the integral. When I take the integral, a natural log of the denominator that's x squared plus 1, and evaluate all that from 1 to t, right? I can pull this 1/2 out front, so I'll do that here. In fact, I can pull that all the way outside of my limit. I still have my limit as t goes to infinity. As I plug in t, I should get natural log t squared plus 1, and I drop the parentheses there because t squared plus 1 is positive. Yeah, so I don't have to take absolute value to make that argument positive. Minus, when I plug in 1, natural log of 1 plus 1 is natural log of 2. And as t goes to infinity there, I'm taking natural log of larger and larger numbers with t squared here, t squared plus 1. The argument is getting bigger, the natural log is getting bigger. Subtracting natural log of 2 has little to no effect, and the 1/2 out front doesn't either. When something is going off to infinity, this limit is infinite. What I can say then is that the integral diverges, which means in turn the integral diverges. So, we typically say, therefore, by the integral test. I'm using that test. That test gives me a result. This series then of n over n squared plus 1 will also diverge, right? So since the integral diverge, we can say that the series also diverges, and the integral test is doing the work for us. So we say by the integral test. Okay? This trend will kind of continue. I'll do this in the rest of the examples, or some of the other examples in this video, and then as we learn different tests, I will use the same kind of terminology and the same kind of verbiage. Is by whatever test I'm using, the series I have diverges or converges, whatever the result. Okay, so there's your integral test. I've shown it kind of twice, maybe just once. I'll do it once more here for us. But before that, there are a lot of series that we would apply the integral test to that we can kind of condense, right? And the harmonic series is actually one of those types of series. The harmonic series is a type, it's a special case, of what we call a type of series called the p-series. Okay, and all of these p-series have the following form. They look like the sum from 1 to infinity of 1 over n to the power p. Right, the harmonic series is, of course, 1 over n, where that's where p, the exponent, is 1. We're considering p to be a constant here. Okay? We have nice convergence or divergence shortcuts for these p-series, right? And I'll show you kind of where these come from. It's just with the integral test. A p-series, we can say, converges as long as p is bigger than 1, and diverges when p is between 0 and 1. Okay, so p is basically less than or equal to 1. We don't really consider negative p because those will always just diverge, right? If I look at the sum of just n squared, all right, I'm adding up numbers that are getting bigger and bigger. Those are going to diverge. Okay, so we don't really consider the case where where p is negative. All of these we can show with the integral test. I'm not going to prove it in general for you. What I want to do is look at one example and then show you how that kind of extends to other examples. Okay, so let's look at 1 over n squared from 1 to infinity as I add those up the series here. All right, this is indeed a p-series where p is 2, which is larger than 1, and I know we just learned this, but that means we expect this series to converge. Okay, let's show that. We'll verify with the integral test. Okay, because 1 over x squared is something that I can integrate very easily. Okay? So sometimes you'll apply the integral test because you recognize that the nth term, 1 over n squared in this case, is something that's very easy to integrate or might prescribe to a u-sub or integration by parts or partial fractions, one of the techniques that we talked about in Chapter 8. Okay, so what I look for, I need to verify those 3 criteria, right? I look at f of x is 1 over x squared. Is that function positive, 1 over x squared? Well, of course, I'm looking for positive x's. The denominator and numerator are both positive. That's an easy one. Is f continuous? Well, not at 0, right? X cannot be 0, but that's not in the interval I'm talking about. F is continuous on the interval from 1 to infinity. That's good enough. Okay? That's what I need. It doesn't matter that it's discontinuous at 0. The third is whether it's decreasing, and for that I look at the derivative. I take f prime. The derivative of f is equal to 1 over x squared should be minus 2 over x cubed. Okay? Is that negative? Yes, it is. There's a negative out front as long as x is positive, right? Because if x is negative, I raise it to the third power, it's negative. That negative and negative will cancel. So as long as x is positive and on the interval from 1 to infinity, that's positive, right? My derivative there is negative, so I can say that f is positive, continuous, and then decreasing. So my integral test applies. I am able to take the integral from 1 to infinity of 1 over x squared dx. It's of course improper. I write the limit as t goes to infinity, the integral from 1 to t of x to the minus 2 or 1 over x squared dx. Okay, this is of course equal to, I keep my limit, antiderivative should be a minus x to the minus 1 or minus 1 over x. Evaluate that from 1 to t. Plug in t, keep my limit, and when I plug in 1, I get 1 there, and I'm subtracting a negative, so that's a plus 1. As t goes to infinity, 1 over t goes to 0, and I add to that 1, this limit is 1. That implies that the integral converges. Therefore, by the integral test, since the integral converges, we can say that the sum of 1 over n squared also converges. Integral test applies. It tells me since the integral converges, so does the sum. And this is true for then any p that's bigger than 1, right? The same effect is going to happen if p is 3. In this case, it was 2. If p was 3, I would take the antiderivative. I'd add 1 to the exponent, and I would get the same effect. That integral would still converge. All right, so it's very easy to show this in general. I just did it with kind of an easy example with p being 2, and show that the integral test applies, converges, therefore the series converges. In general, if you have a series that's a p series, you do not have to do the integral test. Right? You can just jump right to the p series and say, oh, hey, p is 2. That's bigger than 1. The series converges. Okay? Let's look at some examples. The sum from 1 to infinity of 2 over the square root of n. Rewrite this a little bit. It doesn't matter that there's a 2 up here. If I bring that outside, right, that just means that the numerator of every term in my series is going to have a 2. I can factor that out. Keep my sum from 1 to infinity. This 1 over square root of n I can write as 1 over n to the 1/2. The 1/2 is my p. This implies that p is a half. 1/2 is usually less than 1. That's the criteria for a divergent p series. P series diverges. Okay? Easy as that. You don't have to go through the integral test for a situation like this. If you forget the criteria for p series, fine, you can do the integral test, of course, right? But the p series has a nice quick criteria, and it's similar to geometric series, but please be aware of the differences, right? In this case, I have 1 over n to the power p, whereas before I had a times r to the power n. Very different things, different criteria. Okay? Let's do another example. The sum from 4 to infinity of 4 of n to the minus 5/3. That 4, where this thing starts, doesn't matter at all, right? My integral test applies on an interval from k to infinity. So it does not matter that that guy starts at 4, right? Basically, I'm just adding terms further on in my series, right? That shouldn't really have too much of an effect. And that negative exponent takes the n down to the denominator, but still with the power then 5/3. That's my p. P is 5/3. 5/3 is bigger than 1. That's criteria for a convergent p-series. The series converges. That's it. That's all you have to do. P-series is awesome. It's awesome. It's quick. It's easy. Geometric is quick and easy. Integral test takes a bit of time. You have to look at those criteria, make sure your function is decreasing and continuous and positive. Then you actually have to go through the improper integral and find the antiderivative. So you're mixing derivatives and integrals. It's long. It's probably the test that we hope to not have to do. Right. That being said, it paves the way for nice things like p-series. Okay. One more example I want to look at here for us. The sum from 1 to infinity of 1 over the cubed root of n plus 1. Okay, I want you to pay attention here. When I rewrite this, my power in the denominator, I have 1 over, and in parentheses, this n, but it's not just n, it's n plus 1 to the power 1/3. Taking the cubed root is the same as raising things to the 1/3 power. That kills this for being p-series. It's p-series like. 1/3 is indeed less than 1. We do expect this to diverge. But it's very important that this is not a p-series. And I can't stress that enough. This is not a p-series. Okay? It's p-series like. But what we have to do in a case like this, we expect this to diverge doesn't really lie to us in situations like this. But we can't directly apply p-series. What do? We use the integral test. Okay, it's quick, it's easy. Contrary to what I just said, we have an expected outcome. So it's not like we're just kind of reaching in the air for nothing. We have a good idea of what's going to happen here because we can see that power, but it's not a p-series. Okay, so I do have to do the integral test in a situation like this. So some of those might be tossed your way, and you have a good idea of what the outcome is, but you do have to go through and show the integral test. Okay, that's all I want to show you with the integral test here. Just a few examples. Have a decent idea of when they converge and diverge, know those 3 criteria, and be able to identify p-series, right? Those are quick and easy. There'll be a couple of those in the practice, and then on the quiz, and then, of course, the test or the final. Okay? Thank you for watching.